So today we're going to talk about the atmosphere of the sun. So if you're going to recall, we started our discussion with the discussion of the interior of the sun, how energy is generated at the core, and what are the mechanisms and assumptions to estimate how that energy generated from the core or generated at the core is transferred to the surface of the sun. So we already know that from the core, energy is transferred to the center, to the surface of the sun through two diffusion mechanisms. First is the radiation, and then we have your convection zone. And one of the reasons, or one of the important things to remember here, is that because of convection, granulation cells as well as sunspots are often generated at the surface of the sun. So aside from the surface of the sun, aside from the granulation cells, which you already saw earlier, and sunspots, which are magnetically active regions, we can actually also observe some filaments and plages and prominences that is related to the sun. So also, we talked about the solar dynamo and how the solar dynamo is the prevailing model to explain the complicated magnetic structure of the sun. And because of the solar dynamo model, we were able to explain the formation of sunspots, wherein sunspots are actually magnetically active portions of the sun, more active than its normal, wherein from here we could actually observe some what we call the coronal loops. We also had some illustration of how these sunspots are identified from the solar disks. So we call the sunspot groups active regions. So this is the set of active regions that was currently present last September 22. And we have identified five active regions, AR7, 2871, 2872, 2873, 2874, and 2875. And by looking at the magnetogram of the sun, we can actually see that these regions are indeed magnetically active. So from the magnetogram, we can actually describe the magnetic configuration or magnetic classification of each active region. So we can call them alpha, beta, gamma, and delta. So depending on, and you have some assignments about that. And because sunspots are considered to be regions with high magnetic activity, and if we're going to parameterize that presence or quantity of sunspots in or active regions in a solar disk, we come up with the relative sunspot number, and the sunspot numbers actually follow an 11, 12 to 13-year period. And we call that period the solar cycle. And that is directly related to the solar dynamo. So the solar dynamo model basically fairly describes the most common phenomena that are actually happening in the sun. So in the left side, you can see the picture of the sun at extreme UV, EUV, at different portions. So we can see that active regions are actually generate or emit high levels of X-ray as well as extreme UV compared to the regions where magnetic activity is relatively low. So that actually corresponds to emissions of certain elements, okay, which we're going to identify a little bit later. And relative sunspot number is one of the parameters or proxy parameters that we use to describe the activity of the sun. Aside from relative sunspot number, we can also describe solar cycle in terms of its X-ray emissions, in terms of its H alpha emissions. By the way, this H alpha is the red line of the atomic spectra of your hydrogen. If you still remember your modern physics uh, class or modern physics laboratory. You can also follow if you're going to measure the magnesium 2 emission lines of the sun, it also follows the same 11-year period, irradiance, total solar irradiance, as well as the radio flux and sunspot number. So this is radio. This is visible, total visible. These are some spectral lines, and you have your X-ray. So as you will notice here, that as sun becomes more active, the sun emits more radiation across the whole electromagnetic spectrum. So next is we're going to move a little bit farther from the center of the sun, from the core, and now we're going to look at the solar atmosphere. So if you're going to look at, we're going to review the solar structure. So of course, we have your core, radiation zone, convective zone. So these are already considered to be the interior of the sun. And then from the surface of the sun going above, it is usually stratified or layered. It has several layers. We have your protosphere, which is about 500 kilometers thick. And then you have your chromosphere, and then you have your transition zone. And then above the transition zone, you have your solar corona. So these spheres, so to speak, just like your atmosphere, are categorized based on their temperature gradients or how the temperature varies with height from the surface of the sun. And from this atmosphere, we can actually observe several phenomena. We can actually observe from the photosphere, you can see the sunspots. You can also see the granulation cells. And the chromosphere, we can observe some filaments, some prominences, and some flares. We can also do that. No? And then in the transition zone, that's the region with a sharp increase in temperature from the chromosphere to the solar corona. So solar corona are usually observed visually through our naked eye during solar eclipses. But we don't need to wait for solar eclipses to actually observe the sun's corona, because we can actually observe the solar corona through other means. So in today's lecture, we're going to focus on the photosphere, the chromosphere, the transition zone, as well as in the solar corona. Okay, so we're going to focus on this 1, 2, 3, 4 regions. So let's start with the photosphere. So when we talk about photosphere, let's look at the region that is closest to the surface of the sun. If 0 is the surface of the sun, this is the height, okay, from the surface of the sun. And we define the surface of the sun as the region where the optical depth at 5,000 angstrom would be equal to 1. And it is described by a decrease in temperature. Okay. And this layer of the sun is the visible layer of the sun that is seen in white light observations. So if you're going to look at the sun directly right now, what you're actually observing is the photosphere, not the chromosphere, not the transition zone, nor the corona. And it is the region where 99% of the sun's lights and heat is being emitted. Some main characteristics. The characteristics are it is a region where the temperature decreases to a minimum value. Typically, the value of your photosphere, the temperature of the photosphere, is about 6,000 Kelvin at the surface of the sun to about 400, 450 Kelvin, depending on the activity of the sun. And it is reach up about it has a height of about 500, 400 kilometers above the surface of the sun. Majority of the elements that is found in the photosphere is hydrogen by mass. So 74% by mass is hydrogen. Ionization state, because this is mostly plasma. So because plasma is quasi-neutral, so about 100% of this is generally neutral. Okay, the magnetic field is about 0 to 1000 Gauss, or about zero point 0.1 Tesla. So as mentioned earlier, that this region of the sun is the one that is visible. So what we're actually observing from the sun right now is most of it would be the visible range, as well as the other regions of the electromagnetic spectrum. And as you already know from your modern physics class, that the sun's radiance can actually be estimated by a black body at 5,700 Kelvin. So this red line is the estimated black body radiation for temperature at around 5,700 Kelvin black body. Okay, this region is where you can find the visible spectrum. Above that is called the infrared region. Below that is your ultraviolet, and then extreme UV, and then X-ray, etc. So we can actually set this region to be the continuum spectrum. This region is the continuum spectrum of the solar irradiance. So most of the light coming from the sun comes from the continuum spectrum. The rest varies depending on the solar activity. So the UV, extreme UV, X-ray region or spectrum of the sun actually varies with solar activity. If this, for example, is the variations of this region, radiance at these wavelengths or frequencies, during active conditions, this level is actually elevated around this way. Okay, so depending on the variations of the solar activity. Okay, so we can actually observe the sun, as mentioned earlier. Majority of the elements that is present in the photosphere is hydrogen. And these are actually ionized hydrogen or protons. So that means we can actually view the sun at this wavelength. So this wavelength is actually the image of the sun at 617.3 nanometer. This is related to the emissions. So the Fe1, so iron 1 emission lines, okay, which matches the visible light of the photosphere. Usually, we observe the sun, okay, using this image from the Solar Dynamics Observatory. This is generated or obtained from the Helioseismic and Magnetic Imager, or HMI. So when we talk about HMI, the continuum image, we call this the continuum image, HMI continuum. Okay, because it belongs to the continuum spectrum of the sun, and it's actually at the around red region of the sun. So majority of the sun's emission can actually be observed from here. So if we're going to look at the graph of the temperature, the sun can actually observe it somewhere here. Now, as mentioned earlier, hydrogen is the most abundant element in the photosphere. So therefore, we can actually observe the sun through one of its emission spectrum that is described by the Balmer series. If you're going to look at one of the wavelengths that is emitted by an excited proton or excited hydrogen nucleus, okay, we can actually see the sun like this. So this is observed by the Atmospheric Imaging Assembly, or AIA, which is also on board the Solar Dynamics Observatory. Okay, this is what we call the white light continuum at 440 nanometer. This shows the solar surface at about this way, at the surface of the sun, which is equivalent to 6,000 Kelvin. And then if you're going to observe this region of the sun, this is actually corresponds to this wavelengths. This is ultraviolet continuum. Again, it belongs to the continuum spectrum. Okay, so again, going back. So this is white light. So this is ultraviolet. So this is white light at 450 nanometer. It's about blue region. Okay, and then this is also we call this the white light continuum observed at the atmospheric imaging assembly instrument on the Solar Dynamics Observatory, and it's somewhere here in the magnetic spectrum, in the electromagnetic spectrum. So it still belongs to the continuum spectrum. We can also go to the ultraviolet. So this is 170 nanometer continuum spectrum, or wait, yeah, so 170 nanometer continuum spectrum, which is at the surface, which is shows the surface of the sun in the photosphere, just above the photosphere and where the temperature begins to rise here. So this is the start of your chromosphere. Okay, so this is about 4,500 Kelvin. So this is your photosphere. So just to summarize and colorizing things, when you download this data, these images from the Solar Dynamics Observatory database, you can actually see them colorized like this to differentiate them from one another. So anyway, so this is the 170 nanometer. This is the ultraviolet light continuum, which shows the surface of the sun. This is the white light continuum at 450 nanometers. This this is where the surface of the sun that where the temperature is about 6,000 Kelvin. Okay, so this is below the surface of near the surface of the sun. This is a little bit above the surface of the sun. And then if you're going to compare this to the heliosysmic or HMI imager of the Solar Dynamics Observatory, basically picture, these three pictures basically correspond to one another or match one another. Okay. By the way, no, this is the images of the sun at this wavelengths last April 17, 2014. Okay, so that's your photosphere. So again, no, when you look at the photosphere, most of the things that you actually observed are your sunspots. Okay, next, let's go above. So let's go to the chromosphere. So the chromosphere is described by an increase of temperature from the top of the photosphere towards just before the temperature sharply increases. So this is your chromosphere. It is described by temperature of about 4,000 Kelvin to about 10 to the 4, order of the 10 to the 4 Kelvin. Here, 10 to the 4 Kelvin. It is also described as a region where you have a decrease in density. Okay, now comparing this figure here, our earlier figure, the density of the chromosphere is less than the density of the photosphere, and the temperature increases compared to the photosphere. And then, furthermore, we can actually observe the chromosphere. We first observe the chromosphere during an eclipse, because when you have an eclipse, what you can actually see is this red thin layer, okay, that is colored during an eclipse. That's why it's called the chromosphere, because it's actually observed as a color sphere. And if you're going to look at the wavelength that is emitted, the main line or the main wavelength that is emitted by this thin layer around the surface of the sun is about this region. Okay, so this is the sun's chromosphere, which appears to be a dim rim of red lights observed during solar eclipse. Okay, this is not colorized; it's a true picture of a solar eclipse. And if you're going to measure the wavelength of that, that would correspond to the H alpha emission. So that's the red line emission in the Balmer series emitted by your hydrogen. By the way, this is the solar eclipse that was taken in Uganda during a total solar eclipse last November 3, 2030. Okay, you can actually download the image from this. URL. Okay, so if we're going to compare that to the hydrogen emissions, so when you take the spectrum of this wavelengths, spectrum of the chromosphere, the one will peak at this wavelength. So that means majority of the element at the chromosphere is actually hydrogen. Okay, because it emits this wavelength. And if we're going to look at the other spectrum, which I will show, you can actually look over the internet. The H beta, H gamma, and H delta emissions, these four lines, Balmer series lines, are actually observable during the solar eclipse. Okay, you can look at that later. But anyway, the point is that this is one of the important things to look at one of the important applications of the emission spectrum activity that you had earlier before. Okay, so identify the elements coming from certain objects. So comparing it, if we're going to look at the continuum spectrum, and let's say you have a telescope that is directed towards the sun, and then you put an H alpha filter, which is commonly available nowadays, that is an attachment to your telescopes. Okay, so that means your telescope will only observe this wavelength, 656 nanometer. If we're going to look at the sun, it would look like this. This is the image of the sun through an H alpha filter in a telescope at the Lermont Observatory in Australia. Again, this is the same sun. So this is April 17, 2014. That's all. You can notice here, you can see here the observation of your sunspots, even from the chromosphere. But this is photosphere. So if we're going to look at the H alpha, you can see additional features. Okay, you can see these features around it, and you can see extra structures that are now observable at the surface of the sun. Aside from this, you can also observe the chromosphere through another wavelength, through the extreme UV wavelengths. With the help of the Solar Dynamics Observatory, we can observe the sun at this wavelength. This is at 304 angstrom or 30.4 angstrom. So this is actually the light coming from the chromosphere and the transition zone. Okay, and it corresponds to the regions of the sun whose temperature is about 50,000 Kelvin. And if you're going to compare the two, you will see different features of the sun through an H alpha filter and through a transition region. And let's look at this region. Using the H alpha and the extreme UV at 30.4 nanometer spectrum or filter, we can actually observe several things. We can observe filaments. Filaments are mostly observable at the H alpha filter and in this region, in this 30.4 nanometer wavelength. So filaments are dark and thread-like features that can be seen in the red light hydrogen alpha, this red light hydrogen alpha, and even in this region. So these are filaments. Okay, these are dense but cooler clouds of material that are suspended above the solar surface by the loops of the magnetic field. So aside from filaments, we can observe some plages. So it's a French word for beach because it looks like a beach. Okay, these are bright patches surrounding sunspots. So if there are plages, most likely this is near relatively active regions. So usually they can be seen near sunspots. They are best seen in the H alpha filter, but you can actually see them in this region as well. Okay, so plages are associated with concentrations of magnetic fields and form a part of the network of bright emissions that characterize the chromosphere. So this is looking at the surface of the sun. If we're going to look at the animation, so you can see some animated version or how this filaments and even plages evolve over time. So this sunspot region are bright, as mentioned before. are bright in extreme UV. So these are sunspots. Now, looking at the limb, when you had the chance to look at the sun through a solar telescope, you may see something like this. So again, you can see sunspots here. So these are your sunspots. So this is a sunspot. This is an active region. But more prominently, we can actually observe the prominences. So what are prominences? These are dense clouds of material suspended above the sun by loops of magnetic field. You can actually see some coronal loops here, or very, very small loops. In fact, prominences and filaments are basically the same thing. They are just viewed differently. So filaments are the same as prominences. We just call them prominences because we observe them at the surface of the sun, at the limb, and at the surface of the sun, we can look, we see them as filaments. We're going to look at the animation. So these are your prominences. Okay, so, as mentioned, these are dense clouds of material suspended above the surface of the sun. As I mentioned earlier, chromosphere is followed by a sharp rise in temperature and sharp decrease in density. The temperature of this region is about would range of about 10 to the 4 to 10 to the 5 Kelvin or more. Okay, at those order. So we call this a transition zone. This is a transition region from the chromosphere to the corona. So it is very large increase in temperature. Very thin, no? Very, very thin. It's about 8,500 kilometers in thickness. It looks thinner here because the scale at the horizontal axis is logarithmic. The light emitted by the transition region is dominated by the following: emissions from carbon, the fourth line of the carbon emission, that's about 154 nanometer wavelengths. Oxygen 4, so that means that's the fourth line of the oxygen emission, 75 nanometer. And silicon 4, that's a 139.4 nanometer. So you notice that these are all visible in the extreme UV region. So again, review, this is your HMI continuum last April 17, 2014. And this is your graph of temperature versus heights and mass density versus heights, where you can actually differentiate the photosphere, chromosphere, transition zone, and then later we're going to discuss the solar corona. Based on available data, we can actually observe the transition region three ways so far. Okay, we can actually, I will show you three ways. So at this wavelength, this is the carbon 4 plus continuum region. So this is 160 nanometer. So continuum, this is for the photosphere, and this is for the transition region. So what do we mean by this? This figure shows a mixture of light coming from the upper photosphere and the transition region. Okay, so again, the transition region is the region between the chromosphere and the solar corona. Here, the transition region is where the temperature rapid increases. So if we're going to look at this wavelength here, at this temperature somewhere here. So it's just at the start of the transition region, and it also corresponds to this area of your photosphere. So this is a mixture of light coming from the transition region and the light coming from the photosphere. A little bit higher than that, with lower energy, with lower wavelength, with higher energy, that's at 30.4 nanometer. So when you look at this, this is an extreme UV emissions. This corresponds to helium-2 emissions. The temperature of this region is about 50,000 Kelvin. So it's about here. Okay, so this is actually part of the transition from the chromosphere to the lower transition zone. So if we want to observe the lower transition zone and the chromosphere, the sun would look like this. And then going up a little bit upward, okay, so this is 17.1 nanometer or 171 angstrom. This is light coming from the transition zone and a quiet solar corona. So when you see quiet solar corona, that's just the initial part or lower part of the solar corona. So it should be somewhere here. But the temperature is already twice in terms of order as compared to this region. So you will see the rapid increase in temperature from 10,000 at the lower to 50,000 to 600,000 Kelvin. But you can see now at these different regions, you can see the sun with different features. So from this because this is also considered to be a observation of the photosphere, you can see the sunspot as dark spots, but at this region, these active regions, they are actually bright in the extreme UV. You will notice also here that the prominences that can be observed at the 30.4 nanometer wavelength is not observable in the 17.1 nanometer. But the coronal loops that is not too observable in the 30.4 nanometer are already observable in this wavelength. So you will notice here that you can actually see different features of the sun using different wavelengths that is available to us. Okay, now enough about this transition region. Let's go to the solar corona. So this is the region above the transition region. This is usually described by a very hot region, about 100,000 to about a million to 3 million Kelvin. That's how hot the corona is, even hotter than the surface of the sun. So imagine that, no? That's contrary to common sense, where, for example, if you have a bonfire, when you come closer to the fire, it feels very hot. And when you go farther from the fire, you feel less warm. That's very opposite to the idea of the corona. Because here, instead of feeling less warm away from the sun, it will feel hotter. So that's why it's very, very mysterious. And as of now, this heating at the corona is not yet well understood. But that's what being observed right now. No? In terms of order of magnitude, the corona is about 3 orders more hotter than the surface of the sun. Okay, so that's not yet well understood, no? And this is still an emerging field of study in the space physics, specifically solar or heliophysics. Why is corona is much hotter than the surface of the sun? If the corona has a large temperature, the density there is very low. It's about 10 to the negative 12 less dense than the density of the photosphere. Okay, so very, very less. So very, very thin. Okay, relative to the density in the photosphere. Okay, some modes of observation. We can actually observe the solar corona more or less 3 ways. You can observe them during solar eclipse, this one, this area of the solar corona. You can actually observe them using extreme UV or X-ray, like this. And we can also use coronagraphs, which is, I don't know, which uses an artificial eclipse to measure the corona. Because, the photosphere, as I mentioned earlier, the photosphere is, most of the light comes from the sun, it's coming from this photosphere. So that means the light coming from the other regions, especially the corona, is very faint. That's why we have to cover the main source of light, which is the photosphere, to actually see or to emphasize the light coming from the solar corona. And from here, you can actually see different features of the sun as well. So let's start with the white light corona, or an eclipse corona, or a corona brought about by an eclipse. So this is the image of the solar corona during the Great North American Total Solar Eclipse on Monday of August 21, 2017. This is above Oregon. Okay, you can look at this website to look at additional pictures of this certain eclipse. So you will notice here that there are certain features that you can actually observe here. Okay, that this is also this is on top of the fact that we can actually see the solar chromosphere. Okay, so this thin red line, this is the chromosphere, and this white light is actually the corona. Okay. So one of the important features of the solar corona is that can tell us the current magnetic configuration of the sun. Okay. In fact, for example, this is the solar eclipse last August 1, 2008. Okay, this is measured or observed in Mongolia. Okay, so you will see some of the features here. And this actually corresponds very well to its predicted solar magnetic field lines. So this is a solar magnetic field lines that corresponds to the features of the sun. So you will notice here that it is very evident that bright features in the white light corona correspond to the regions with close magnetic field lines. Okay. As if you still remember before when we started discussing, or I started to introduce to you the magnetic configuration of the sun, we can see several components here, no? You can see the radial components of the solar magnetism, solar magnetic field. You have your dipole component, this one. Kita nyo ba? Sorry, back. Going back. Okay, so this is your radial. So this is your radial magnetic field lines. Okay, this is your uh, sorry about that. Again. So this is your dipole components. And then you have your neutral sheets, which corresponds to this region. So we can actually observe this because these are actually emissions from the plasma that is trapped within this magnetic field lines. Okay, so again, going back to this picture of this solar eclipse, from here we can actually see several features of the solar corona. We can observe what we call the helmet streamers. It's called the helmet streamers because these are cup-like, mukhang sombrero, no? These are cup-like structures with long pointed peaks. These are streamers because these are fairly wide at the surface of the sun, wide here, and then it tapers off away from the sun. So these are what we call helmet stream. This is the most common of all coronal structures that we can observe. Aside from that, we can actually observe here these polar plumes. These are bright structure of fast flowing solar material, a fast flowing solar plasma coming off the poles. Okay, which is guided by the polar components or radial component of the sun's magnetic field. This is associated with these open magnetic field lines, and these open magnetic field lines are connected to the interplanetary magnetic field, which we're going to talk about in the coming days. And this is commonly found in corona holes, okay, which we're going to talk about later. Aside from this, we can also observe some coronal loops. So these are the coronal loops. If you can see, not this one, not this one. This is part of the chromosphere. This is the coronal loops, which is associated with sunspots or active regions. Okay, and they have close magnetic field lines. So that means the magnetic field lines coming from the surface of the sun is close to the surface of the sun as well. Okay, they connect surface to surface. Okay, and then just to complete the picture, we can also observe your prominences. Okay, these are prominences that is part of the solar chromosphere, of the chromosphere. So this is your H alpha emissions from the chromosphere, which we can use to observe these prominences. This is happening during a solar eclipse. Now, how about if you want to observe that in X-ray. So again, this is your continuum at two different times. This is today, yesterday, September 27, and then this is April 17. So you will notice here, no, this is two different moments of the sun. This is the moment where the sun is active in terms of, this is high solar activity. This is during low solar activity, which is, how do we know? Basically by looking at the sunspots. So relatively, this is a low solar activity. Sun during low solar activity. This is the sun with high solar activity. And if we're going to use 193 angstrom wavelengths feature or image of the sun, or 19.3 nanometer, the April 17, 2014 sun would look like this. So as I mentioned earlier, again, sunspots will appear bright in extreme UV. So this is extreme UV. And then yesterday, the sun looks like this. So you can see the contrast between the two. So this wavelength is actually used to observe the solar corona. By the way, again, the wavelength that we use here is 19.3 nanometers. That's 193 angstroms. So this shows a slightly hotter region of the solar corona and also much hotter material of the solar flare. So we can actually observe solar flares using this wavelength or image of the sun. Okay, so let's look closely. We can see additional structure. The solar corona, we can see corona holes. Corona holes are characterized by low density of cold plasma, and they appear dark in this wavelength. Okay, it's about 500,000 Kelvin colder than the bright regions. So when we say bright regions, these are bright regions, and they are usually the source of open field lines, which I mentioned earlier. So these bright regions are observable if you have a quiet sun. So it appears this intensity at this wavelength when you have a quiet sun. And if the active regions of the sun, it will appear brighter. Speaking of that, you can see the coronal loops here. So these are your coronal loops. So these are your active regions. They appear bright in extreme UV. They have curving structures that appear as arcs above the solar surface. This contains hot plasma. Okay, so when you have a hot plasma, that the energy that the photons that it emits have shorter wavelengths with higher frequencies, and they are usually found in sunspots or active regions. If we're going to combine these features, so to this white light, so we can superimpose that disk over here. So the solar plumes emanate from your coronal holes. Okay, and then your coronal loops would look like this. And then your bright spots or bright sun or quiet sun, which is it looks hazy for this region, looks like this. The solar corona basically has the structure. You have your polar plumes, you have your corona holes, you have your helmet streamers, you have your corona loops. The corona loops and the limb can be observed like this. And then at the surface of the sun, it can be observed like this. Okay, again, this is for August 21, 2017. These prominences are just an extra. This is actually not part of the solar corona, but parts of the chromosphere. But when it is ejected, it becomes part of the solar corona. So as I mentioned earlier, as you can observe the sun, we don't have to wait for a solar eclipse to observe the streamers or the limb part or this part of the corona, because we are currently observing the sun using coronagraphs. These are pictures of wherein an artificial eclipse is done. So if you have your sensor or camera here, we cover the sun with a cover whose radius about 2.5 times the radius of the sun. So imagine this is the size of the sun. So aside from covering this part, we can actually cover this great part so that we can actually observe this. It looks, I don't know, this is the same date, no? August 21, 2017. In order to do this, if this is your solar corona coming from the telescope, what you can actually observe here is if you're going to reverse this. And then if you're going to animate, we can actually see some streaming here. So that's why it's called the streamers. So we can actually observe some emissions of plasma at the streamers. So just to give you an idea, no, these are your streamers that can be observed via the coronagraph. So this streamer is the streamer. This streamer is the streamer. And then this streamer is actually this streamer. Okay, so let me just play that again. Okay, again, let's play that again. What is this? If I'm not mistaken, this is Mars. This is Mercury. Anyway, we can actually observe another coronagraph. There's another version of the coronagraph with a wider view. So we call that the C3. This is C2, no? This is C3 coronagraph. So we can actually observe the streamer more prominently. We use the coronagraph to observe how plasma is ejected through the sides. In the perspective of this, no, in this perspective. So combining these features, okay, we can actually observe additional features, no, additional transient features of the solar corona, and even the surface of the sun. Okay, those two are what we call your solar flares and coronal mass ejections. So this picture of the sun is at 193 angstrom last July 7, last July 3, 2021. So if you're going to observe that, you can see there are bright flashes here. Okay, if you want to look closely, so you can see some bright flashes in this active region. Those are actually solar flares. Again, no, these are actually solar flares. So there's a bright flash of light in extreme UV, this wavelength at this region. I can actually observe this one. So this is a bright flash in extreme UV. By the way, this is not in real time. When I say it's not in real time, no, the time scale is very fast. So if you're going to notice here now, this is just a fast forward view of the sun. But anyway, this feature actually correspond to this one. This one is actually this one. So this is about 17 UT. Okay. Looking at this coronal graph, so we can see that emission. Okay, so this solar flare actually emitted a gas. We call that emission of gas, ejection of gas or plasma as coronal mass ejection. If you're going to trace somewhere just after 17 U, just around this time, so we can see the ejection of the sun. So there was an explosion here. And that will be our next topic, next meeting. Solar flares and coronal mass ejections.